Hi, welcome back to Stats class with Dr. Howald. Today we're going to be talking about multiplying probabilities, a simple solution strategy for solving a lot of interrelated problems, but one that doesn't always work. We'll have to talk about when it works, when it doesn't, and what to do differently if it's not in the right kind of situation that it's going to work that way. So let's start with a simple example. Suppose that I have 5 coins. So I'm using $50 for visibility here. Supposing I have 5 coins and I want to take all these 5 coins in my hand and I want to flip them all. And I'm going to ask the obvious probability question here. What's the probability of certain outcomes? The outcome that I'm interested in is getting heads on all 5 of the coins after I flip all of them. Now, it's not very likely, so we should expect the probability to be a pretty small number. So let's think about a simpler problem. Let's think about 1 coin. When I flip the coin, the probability is 50-50 or 1/2 or 0.5, however you want to express it. Now, what that means is that half the time I flip this coin, it's going to land heads, and half the time I flip this coin, it's going to land tails. If I'm flipping 2 coins, then if this one is only heads half the time, then the other one is going to reduce the amount of time that we get 2 heads by another factor of half. So the probability of getting heads on 2 coins is going to be half of a half, or 1/4. The probability of getting heads on 3 coins, when I flip 3 coins, is going to be half of a half of a half. And so we get 1/8. And then with 4 coins and 5, then we continue this process. We get 1/16 for 4 coins and 1/32 for 5 coins. What I'm doing here is I'm applying a multiplication of probabilities formula, which is the top formula behind me. This formula tells me if you want the probability of multiple things simultaneously happening or happening one after the other, then the probability can be calculated by just figuring out the probability of each of them and just multiplying them. And that's all I'm doing with the coins. I'm just taking each individual coin has a probability of 1/2, and I'm just multiplying a half times a half times a half times a half times a half to obtain the probability of 1 in 32. And this is the correct answer to the coins problem. The probability of getting 5 heads, all of them, is exactly 1 in 32. Now, that's the correct answer unless I play some silly games. But I want to call your attention to one of the silly things that I could do here, which is obviously not the intention of the problem. One of the things I could do here is I could tape all 5 coins together. I could tape them together in a block and flip them as one. Now, if I do that, of course, that would not be the same experiment, but if I do that, I am still technically flipping 5 coins, and they either all land heads or all land tails, depending on how the block lands. So that would be cheating, right? And that would change the answer. But the important thing is, like, how would that change the answer? The answer would then become 1/2. Why would it change the answer? Because the coins are no longer really separate events. The probability for this coin, the top coin in the stack, landing heads is 1/2, and the probability that the bottom coin lands heads is also 1/2, but they're no longer separate. And so it's no longer appropriate to multiply them. So here we get our first kind of inkling that there's something wrong with this formula if the events are interlinked or literally taped together. Okay, next example. I want to do an online magic trick. Okay, how this is going to work is I'm going to hold up some colors. These represent 3 colors. We got blue, we got red, we got green. I want you to pick one in your mind. Okay, don't tell me which one because it's a video. Pick one in your mind and stick with it. Okay, make your choice. All right, cool. Now, call this coin flip, heads or tails. What's it going to be? All right, just in your mind. All right, stick with your answer. Okay, here's my magic trick. It's a psychic magic trick. You picked blue and you picked heads. Pretty amazing, right? So most of you are probably thinking, what the heck kind of magic trick is this? But a few of you are thinking, whoa, cool. Why? Because this is not a magic trick at all. This is just me randomly guessing, but I have a certain probability of being correct in those random guesses for a certain portion of the audience. And if that includes you, you might be impressed or maybe not. The question here, the probability question is, what's my probability of being correct if I have no psychic abilities at all, but I'm just randomly guessing what you picked? Well, the probability of me guessing the color correctly is 1 in 3. The probability of me guessing your choice for the coin flip correctly is 1 in 2, assuming I don't know anything about your psychology. So the 1 in 3 times the 1 in 2, those give us 2 probabilities, and the probability of me being correct in both of these choices is then, of course, 1 in 6. So that gives us a total probability of 1 in 6, which means approximately 1/6 of the audience has an opportunity to be impressed with this not very impressive magic trick. Now, I want to make a subtle change to this problem, and I want you to think about how it might change the answer to my odds of success. Pick one of three colors, okay, but now instead of choosing a coin flip, I want you to simply choose between two temperature ideas, the idea of hot or the idea of cold, okay? Now that is superficially exactly the same problem. You're making a choice among two, heads or tails, hot or cold, it makes no difference. But we have associations, mental associations between colors and temperatures. We would tend to associate the color blue with cold, and we would tend to associate the color red with hot. And that means that if I might know something about your psychology, maybe, maybe not, but you might be more likely to choose the temperature cold if you had chosen blue, and you might be more likely to choose the temperature hot if you had chosen red. I don't know that that's the case, but it might subtly change the odds, which means that if I guess now that your selection is blue and cold, I might have a somewhat better than 1 in 6 chance of being correct because I might have predicted something about how your psychology works. So here, like the coins, we have two kind of versions of this problem. One version in which they are truly separated and unrelated, and one version in which there is a subtle linking here between the one choice that you make for the color and the secondary choice that you make for the temperature. If the events are completely unrelated, completely disconnected, like the coins not taped together, then it's correct to multiply the probabilities. But if there is a relationship between the events, then it's potentially incorrect to multiply the probabilities. All right, another simple example. This is my phone. It has a PIN, of course. You have to type in the PIN correctly in order to unlock the phone. Most people's phones work this way. If we assume for the sake of argument that it's a 4-digit PIN um, and that each digit is of course between 0 and 9, then there are 10 options for each digit. If you pick up the phone and immediately try to type the PIN, having no information at all about what the PIN is, what's your probability of guessing correctly? Well, not very good. I could try to calculate how many possible pins there are, but I want to treat this as a probability problem instead. So what's the probability that the first digit is correct? Well, 1 in 10 because there are 10 possible first digits. What's the probability that the second digit is correct? 1 in 10. Third digit, 1 in 10. Fourth digit, 1 in 10. So we agree that the odds of getting a correct guess for each individual digit are 1 in 10. What do we do with 1 in 10, 1 in 10, 1 in 10, and 1 in 10? Well, if we add them, we get 4 in 10. That doesn't sound right. The correct thing to do here is to multiply them because in order to guess the PIN correctly, they all have to be correct. So we will multiply the probabilities 1 in 10, 1 in 10, 1 in 10, 1 in 10, which is the same as multiplying the fractions 1/10 times 1/10 times 1/10 times 1/10, which gives us 1 over 10 to the 4, which is 1 in 10,000. So the probability of guessing the PIN correctly, if you just randomly guess the PIN, is 1 in 10,000. For most uses, that's adequate security. But there is, of course, this disturbingly real probability that anybody can pick up this device and type the PIN just at random and get it correctly with a probability of 1 in 10, 1 in 10,000. If I'm not happy with that probability, if that's not secure enough for me, then I need to use a longer PIN. If I use 6 digits, then instead of 1 in 10,000, we multiply by 1 in 10 again and 1 in 10 one more time, and we get 1 in a million, which is, feels more secure. Why is it safe to multiply in this case? Because your probability of guessing the first digit correctly is unrelated to your probability of guessing the second digit correctly, because there's no relationship between the digits, at least no presumed relationship between the digits. If you have some psychological information about things I would likely choose, then that changes the entire ballgame. And we no longer are dealing with a probability of 1 in a million. We would now be dealing with a different probability that would depend on my psychology and your ability to guess it. All right, next question, which may or may not be identical to the first question. The next question is about alligator eggs. So alligators lay eggs, and this is, I confess, not an alligator egg. This is an ordinary chicken egg bought from the grocery store. An alligator egg looks like this, except it's just a bit larger. It's kind of elongated compared to this. Usually white. This one's brown. Alligators lay eggs, they lay fertilized eggs, and then those eggs, of course, hatch later. And when they hatch, there are two sexes that can result. You can get female alligators or you can get male alligators. So I want you to imagine that we have a clutch or a nest of five alligator eggs. I've only got two here. I want you to imagine that we have five alligator eggs, and we're interested in what might happen as the eggs hatch, whether we might get female or male alligators as a result. So you would probably expect the most likely outcome is a mix, and that would make sense, right? A mix of some female and some male, maybe two female, maybe three male, I don't know. So you would probably expect a mix. Is it possible that you could get all female eggs from one nest? Well, yeah, it is actually possible that you could get all female eggs from one nest. We could calculate the probability of that. Let's do it in the same way that we did it for coins. So the probability that the first egg is female is going to be 1/2. The second egg needs to also be female in order for us to get 5 female eggs. And so the probability that that hatches and produces a female alligator is 1/2. The third egg, the fourth egg, also 1/2, 1/2. And so this is the same problem as the coin problem, right? Because we have a half and a half and a half and a half and a half. And in order to get the event of all female, well, we need all of those events to occur simultaneously. And so because we need all of them to occur, we multiply the probabilities. A half times a half times a half times a half times a half. And the probability that 5 alligator eggs hatch and produce all female nest is going to be 1/32. Now I want you to look for the hidden assumptions of this. Look for how this is and is not the coin problem, right? I'm making certain biological assumptions. The first and most obvious is that I'm assuming that all of these eggs are viable and hatch, right? If some of the eggs don't hatch or get eaten by other predators, then that's not going to work. So I'm assuming that all of the eggs hatch. I'm moreover assuming something about the biology of alligators. And what I'm assuming is that each individual egg has a 1/2 probability of producing a male or a female. Now, I don't actually know that that's the case, and that's an interesting biological, ecological question. What's the probability of each sex result among alligators? Let's take for granted that it's about 50-50 and that estimating this at 50-50 is fair. I mean, it's a mathematical model. It's probably not exactly 50-50, but it's probably a fair thing to do in solving this problem. So we've talked about the assumption that the eggs hatch, the assumption that the sexual breakdown of like how many females and males you have in the species is about 50-50. But there's one other assumption, which is really hard to spot here. And it corresponds to the assumption that the coins are not taped together, right? Is this or isn't this the coin problem? That assumption is that the sex result of the first egg, whether it's female or male, has nothing to do with the sex result of the second egg, whether that's female or male. And it's hard to recognize that this is a real assumption in the problem. It's hard not to just say, well, of course, like how could it possibly be related? Because these are like genetically distinct things and each one of them is random. How could there be, I mean, there's no biological connection between the eggs, right? There's no biological intercommunication. There's no proteins going back and forth. There's no obvious connection here by which the eggs would communicate this. And besides, even if they could communicate, isn't this genetically determined? So wouldn't it just be determined from the very beginning anyway? So, well, actually, no. So this is the reason why, for this example, I chose alligators, because there's a striking and surprising thing about how alligator sex distinctions are made. When the eggs are laid, they are fertilized, but they are not determined as male or female. In fact, that feature of the hatchlings is not determined until about week 3 or 5 of incubation, when it is determined by the temperature of the nest. If the nest tends to be on the colder side, then the eggs tend to hatch female. And if the nest tends to be on the warmer side, then the eggs tend to hatch male. And that's not hard and fast rule, you can get nests where you have a mixture of females and males, but this is a pretty strong tendency of the eggs. And if the eggs come from a nest that is particularly cold, there's only a few degrees difference between virtually guaranteed all female and virtually guaranteed all male, which is kind of peculiar and surprising. And, like biology is full of surprises, right? So what that means is that, yes, this is analogous to the coin problem in that we have 5 probabilities, and each one of them really is 1/5. But it's more analogous to the coin problem in which the coins are all taped together because the temperature of the nest is the real determining factor, which half the time may be too cold and half the time may be too warm, and therefore half the time producing each each sex. Um, Now you might say, okay, well then I've hidden the variable here of the temperature of the nest, which is the real random variable here. But I would say even without understanding the temperature of the nest, we can still say that there's a relationship between the genders of 2 eggs. You see, if you know that one egg is female, then you should be able to make valid inferences about the environment in which it's hatched. If this egg is female and it comes from the same nest as the others, if this egg is female, then it is correct, not guaranteed correct, but likely correct, to make inferences about the temperature of the environment in which it hatched. If this egg is female, then it probably hatched in a cold environment. And if it did, if this one did, then the other one probably did too, right? Because they're in the same nest. So if this one is female, it is correct to infer that it hatched in a cold environment. Not guaranteed correct, but probably correct. And then this egg, which was right next to it, then also hatched in a cold environment and is also probably female. So once you know that this one is female, it is correct to deduce that this one is probably female. And that means that the calculation 1/2 times 1/2 times 1/2 times 1/2 times 1/2 is completely wrong for the alligator eggs. In fact, that predicts a probability of 1 in 32 that the entire nest would be all female. But the probability of that event is far higher. It's more like 1 in 4. It's far higher than that because all it takes for that to occur is a cold nest, which is actually much more likely than 1 in 32. So we see here that there is a formula for calculating the probability of several things happening at once. The probability of A and B is the probability of A times the probability of B. But in the case of the alligators, that formula is wrong. It's wrong because the event A and the event B, the sex of the first egg and the sex of the second egg, are not independent events. This strategy of multiplying probabilities is correct when the events are independent, but it is incorrect when the events are somehow related. So this notion of dependent or independent is actually very difficult to, it's difficult to tell whether events can be independent or dependent. And I want to do another example where it's not obvious whether these should be treated as independent or dependent events. So here's the next example. So I'm gonna fan out the cards and we'll play the usual magic trick and I'll pick a card and I won't tell you which one, okay? And now you're gonna be the magician and then you're gonna have to figure out what the card is. Okay, this is not a fair game, but you're gonna guess, right? I wanna ask you 2 questions about the card and then the real question is what are the probability of these questions having certain answers? So the first question is the card a queen? And the next question is, I'm not going to ask about the suit specifically, but the color. Is the card red? Okay. So maybe I want you to imagine some sort of process or some sort of magic trick that depends on me drawing a card, but it has to be red and it has to be a queen. Okay. Who knows what? There is some probability that the card is a red queen. And we can ask, what is that probability? Now, that's not especially hard to calculate. There are 52 cards and there are 2 red queens in the deck. So it's 2 out of 52, which simplifies to 1 in 26. This is a valid way of calculating it, and sure enough, it's 1 in 26 that this card would be a red queen. But I want to explore whether we can do this by multiplying probabilities instead of just counting the successes. So what I did when I solved the problem, I basically counted that there are 2 successes, counted that there are 52 possible outcomes, and I did a division problem. I'm not multiplying probabilities, so that solution doesn't fit in this video. Let's try to find a solution that does fit into this video. So I want to think separately about whether the card is a queen, and then whether the card is red. So let's only ask the question of whether this card is a queen. Now, that question has a probability yes, which is easy to calculate because there are 13 different face values on the cards, and one of those is queen. So to the question, is the card a queen, we have a probability 1 in 13. Now we have a secondary question, is the card red? Half the cards in the deck are red and half the cards are not. And so to the question, is the card red, we have the answer, the probability 1/2. Now, here's the kicker. I want to combine these because I want not just a queen, not just a red card, I want a red queen. So I want both of these things to be true. So I'm going to apply the law. The probability of A and B is going to be the probability of A times the probability of B. Here, A is being a queen, B is being red. So the probability of A is 1 in 13. The probability of B is 1 in 2. So I'm taking the fraction 1/13 and multiplying it by the fraction 1/2, and I get the fraction 1/26. Now, was that valid? We've seen in the cases of coins that multiplying probabilities is perfectly fine. And in the cases of alligator eggs, that multiplying probabilities is not so good. And the difference is that in the case of the alligator eggs, these probabilities are dependent. The events themselves are dependent on one another. They're interrelated. They're affected by other things. They're not distinct events. They're not completely unrelated trials. In the case of the coins, when I didn't tape them together, they're completely distinct. They're unrelated events. We call them independent. Now, the question here, am I entitled to take the 1/13 and multiply it by the 1/2? The question really boils down to, is the event of being a queen independent from the event of being red? And this is now suddenly not such an easy question. You could say, no, they're not independent because there's only one card drawn from the deck, and it's that card which determines everything. But then again, you could make another argument that the color of the card and the face value of the card are basically unrelated features of the card. There are equal numbers of red queens and black queens. There are equal numbers of red cards and black cards. So which argument is correct? They're dependent events because there's only one card and we're describing the card with two different features of that card. Or they're independent events because the face value of the card and the color of the card have nothing to do with each other. So this is not so easy, right? And it's not so easy to tell whether the application of the multiplication formula was correct or incorrect. But fortunately, we have the right answer to the question already. It's 1 in 26. And so if we multiply the 1/13 by the 1/2, we can see that that doesn't indeed give us 1 in 26. That suggests that it's correct to think of these as independent events on the card, even though there's only one card. Why are they independent? Fundamentally, because the color and the face value are unrelated. If all the queens were red, this argument would not be valid. But half the cards are red, exactly, and half the queens are red, exactly. And that means that being red is basically unrelated to the question of being a queen. So that's why the color of the card and the face value of the card in the structure of an ordinary deck are independent events. And it is, in this case, safe to multiply the probability of being a queen times the probability of being red, and that will give us the correct answer. Next example. I want to talk to you about a dice game. Statisticians' dice games are always very simple and boring because we don't want them to be too complicated. We want them to be really simple. So here's a hypothetical dice game. We have two dice. You get one, I get one. I'll roll the blue die, you roll the green die. How does the game work? If we each roll the die just exactly once, if we get the same answer, it's a tie. If my number is bigger, I win. If your number is bigger, you win. It's a really boring, simple game. Okay, so this is the simplest dice game you could have between two players. Each roll a die, higher number wins. I guess it can be a tie if the numbers are equal. Now, let's suppose that we play the game and I'm cheating because I'm doing it off camera. Ooh, I rolled a 5, okay? Oh, too bad, you rolled a 3, okay? Now I want to describe this event and then I want to say what are the chances. So I'm going to describe this event this way. I'm going to say I rolled a 5 and I won. Okay. Notice that I'm not fully describing the event. I'm not describing what you got. I'm putting it in the context of what I rolled and also what was the result of the game. I rolled a 5 and I won. And now I want to ask, what are the chances of that outcome? What are the chances of an outcome in which I roll a 5 and I win? Now, we can easily calculate the individual probabilities of those separate events. So what's the probability that I roll a 5? Well, that probability would be 1 in 6. What's the probability that I win the game? Well, it's not so easy to calculate the probability that I win the game, but take my word for it, the probability that I win the game is 5 in 12. The reason for this is that it's half of all the outcomes in which we don't tie, and so it's 5/12. Now, is it correct for me to say the probability that I win a 5, sorry, that I roll a 5 and win is the product of those numbers? The probability that I roll a 5 being 1 in 6, and the probability that I win being 5 in 12. Can I just multiply those to find the probability that I roll a 5 and win? Well, absolutely not. That would be wrong in this case. Why is that wrong in this case? Because the events are subtly connected. Because if indeed I roll a 5, then that's a pretty good roll, and then I'm more likely to win. So here we see the dangers of using the multiplying probability strategy. The fact that I rolled a 5 changed the probability that I won in the same way that the fact that this egg was female changed the probability that this one was. Under these conditions, it is not correct to multiply probabilities, and you will get the wrong answer this way. So if I take just in a vacuum the probability that I roll a 5 and multiply by the probability that I win, I will get the wrong answer to this problem. What I need to do instead is I need to start with the probability that I roll a 5, which is 1 in 6. And then I need to reason about the probability that I win, but I need to reason about that probability assuming that I rolled 5. Let me say that again. That's a tricky point. I need to multiply the probability that I roll 5 by the probability that I win, but when I assess the probability that I win, I need to take into account the fact that I rolled 5. How do I do that? Well, the probability that I rolled 5 is, again, easy. That's just 1 in 6, no problem. What's the probability that I win taking into account my roll? Well, that's actually not too bad. If I take into account my roll of 5, then I will win if you roll 1, 2, 3, or 4. That's 4 out of the 6 possible outcomes that you could roll, which makes 4 in 6. So I need to take the probability that I roll 5, 1 in 6. I need to multiply by the probability that I win, taking that into account, which is 4 in 6. So I take 1 in 6 times 4 in 6, which simplifies down to 1 in 9. So the probability that I roll 5 and win is 1 in 9, or 1/6 times 4/6. So this modification of the multiplication rule is critical in any kind of situation where the events are potentially interrelated. So for example, with the alligator eggs, I can use this, if I have enough information, I can use this more successfully. I can take the 1/2 probability that this is female, and then when it comes time to multiply by the probability of this being female, I don't use 1/2. I take into account the fact that this one is female. And I say, okay, given that that's female, then that changes my assessment of whether this one is likely to be female. And I get a different probability that this one is female, perhaps 0.9, right? It probably is, right? Now, figuring out that probability exactly would be a challenge. But if you can do it, the right way to do it is to figure what is the probability that the second egg is female, given that the first one is. And then when we get to the third egg, we should be asking, what's the probability that the third egg is female? But we should be asking that in the context of the knowledge that the first two eggs are female, which gives us extra evidence that the third one is because of the interrelationship with temperature. So let's do a summary here. It is correct in many problems to calculate the probability of a chain of events by simply multiplying their probabilities, as we saw in the coins and the magic trick and guessing the pin. We take the probabilities of each individual event and then we just multiply them together to calculate the probability of some overall event. Even if, in the case of the red queen, even if the events are really descriptions of the same thing, as long as they are independent, then it is correct to multiply the probability of one kind of event times the probability of another kind of event and get the probability that everything happens as described. The problem comes when the events are dependent or interrelated or correlated somehow. If the events are connected so that one of them causes the other one to be more or less likely, then it is not correct to just use this multiplication problem and the formula, and it will give us the wrong answer. So what do we do instead? We modify it, and that's the lower formula here. The probability of A and B is the probability of A times that weird thing. That says the probability of B given A. The vertical bar is read given. What that means is you have to figure out the probability of that secondary event, B, but when you're figuring out the probability of that secondary event B, you need to be correctly taking into account the assumption that the event A has occurred. So that probability there, the probability of B given A is the assessment of how likely B is under the assumption that A has indeed occurred. And if the events are related, that will be usually different from the probability that B occurs just without any given information. So that's how we have a formula for calculating the probability of a chain of events, when it is correct and when it is incorrect, and what to do in case that formula fails. Thanks. Have a great day.